This lecture is taken from my Fundamentals of Operating Systems course. This is specific to asynchronous I/O or non-blocking I/O. So I hope you enjoy it. I dive deep into how what's the main problem of blocking I/O and how the Linux kernel addressed it by introducing many iterations of solutions until they reach to a stable one. This is a detailed rundown of how EPOL works, and if you notice in our system trace operation through node, we see that how EPOL is being called very frequently in most Linux systems. So I encourage you to watch this lecture to get a fundamental understanding of asynchronous I/O. It's a really powerful concept. Let's jump into it. All right, one of the most important lectures, asynchronous I/O, non-blocking reads and writes. Okay, guys, we're going to talk about EPOL, talk about all these beautiful things that we have. Most I/Os in the kernel is blocking. What does that mean? It means that read, write, and accept and multiple other syscalls are actually blocking. It means that the moment you send it, you cannot move your program counter. You're stuck. And most probably you're going to be context switched out from your beautiful core if you make any of these calls, because it's a blocking and you cannot do anything about it. You have to wait. You have to block. You cannot move to the next line of code. You're technically synchronously blocked. Right there. Here's a beautiful line of code. I want to execute it. Nope. You made it. You made an I/O. It's a blocking I/O. You ain't moving. And I'm not talking about async await and none of this. This is actual blocking, right? So that's the process, making call to a kernel and then it's blocked. So the read blocks, example, a read, POSIX read, will block when there is no data in the receive buffer. And accept will blocks when you have no connections. And if you read and there's a file, you don't really technically block, because the file, unless maybe it's locked by something, it will be available. If it's available, if you're reading a file from this, you're essentially be blocked, but blocked in a sense because reading from file is so slow that it will also consider be a blocked operation. But there is a finite block amount here. Blocking from a receive buffer, reading from a receive buffer in kernel network speak, will block you as long as there is no data. When the moment you have data, you'll be unlocked, and the data will be moved to your data. And of course, it leads to context switches and slows down. Here's an example I did. Let me disappear. So here's an example. Here, let's do some legend explaining here. This is first of all, this is just pseudocode. That's not real. I just want to, first of all, to write the code here. It won't fit into a slide. Second, it will, there's so much stuff and it's really hard to parse and read. So read takes the connection. I'm having a loop to loop through all the connection and reading and putting it in a buffer. That's all what I'm doing, right? So this is a system call. And here, the legend, these are packets or content or data in the receive queue for that connection. So green is there is data, gray means there is no data in the receive queue. So we have 10 connections for that particular socket I'm reading from, right? And I am a single process responsible for reading from all those file descriptors. So what will happen? I'm gonna read connection 1, successful immediately, non-blocking, because there is data. Read connection 2, non-blocking. But read connection 3, I'm blocked. And let's say client 3 is just sleeping and never send any data. I'll be blocked forever. Well, until the client 3 sends something. But there is connection 4 and 5 and 6 and 7. What happened to those? Well, I'm sorry, I cannot go to the next program counter. I cannot increment my program counter. I'm stuck. That's how a blocking operation is. You cannot continue the loop. Right? Look at that. That's really bad, right? You don't want that. You don't want to block. You want to be able to at least know that, oh, if there's data, read it, else move. At least something like that, right? And that's what async gives you. Right? So that's bad. We know this is bad. We don't want to do it. So meet asynchronous I/O. So read blocks when there is no data in the receive buffer. We talked about that. And accept blocks when there is no accept in a collection in the queue. So there are certain ways to solve this. And I'm going to talk about 2 ways here. And none of them work with the storage approach. Right? Well, at least this doesn't work with the ready approach. Doesn't work with the storage. The completion, maybe. Yes, we'll talk about that. The ready approach, you do this. You ask the OS to tell us if a file descriptor is ready. And by ready, that's ready. That's not ready. That's ready. That's not ready. Right? That's the readiness concept. Yeah? So when it's ready, we call it without blocking. And this is how KQ work in Mac and how epoll works and select works in Linux. We'll go through them. Don't worry. We'll do it. So that's the ready approach. You ask if it's ready. If it's ready, you read. You don't perform the system call. You only perform it when you get a notification from not notification when the kernel tells you it's ready. Right? So there is still a system call technically that is checks. Is it ready? Is it ready? Is it ready? Is it ready? Right? But we're gonna make it better. But still there is this is it ready? Is it ready? Is it ready? Thing. Completion approach is you ask the OS to actually do the work for you and notify you when it's completed. So you submit a job, the kernel does the job, and it writes back the result. You don't do anything. You just moves on. And that's how Windows work, I/O completionist port, and that's how I/O ring work. Basically, you send a submit queue, and there is a completion queue. Right? And as we talked about it, this doesn't work with storage stuff, like because a file doesn't become ready, right? It's ready. It's always ready. It just takes time. This epoll doesn't work with files, right? You need a completion approach to work with files, essentially. All right. Let's talk about select, which is the first design that they built to solve this problem. So select takes a collection of file descriptors for the kernel. So the select takes a collection of file descriptors for the kernel to monitor. It says, all right, hey, kernel, I'm interested in these 10 connections. Monitor them, please. Right? Monitor them if they are ready or not. Then what happens here is you call select and you give it a timer. Say, all right, call select. And I would be, hey, I'm interested in these. I want to, actually, to be honest, there is a read file descriptors. I'm interested to read those. I'm interested to write those. I'm interested to accept those, right? Certain things from him. Right? So there's like a specific thing, but I'm going to simplify and say, all right, I'm interested in these file descriptors. And tell me if they are ready or not. So if there is at least one that is ready, the kernel will return. I said, all right. So you still need to call this select thing with a list or the set of file descriptors. Every time you call it, and if there is one thing that is ready, you're gonna get back. You'll immediately return, right? Then the process actually need to check, like which one is ready. That is a loop. And you need to call this thing called FD set. Like you got, is it ready? Is this one ready? Is this one ready? So you can see that this breaks up really. Like, okay, first of all, you want to call, and I have 10 connections, and let's say one of them is ready, 9 is not. Then you have to loop, which is big O of N, to find out which one is the one that is ready. It doesn't tell you. The kernel doesn't tell you which one is ready. Remember, this is the first one. This is the first attempt to asynchronous IO. So you have to loop to find out which one is ready, and you have to call it is set, and it will tell you, oh, is this one is set, and this one is actually return, right? FD, and it will actually return the FD set in whatever, like, because you have to pass in a set. And it will tell you, is this one ready? Is this one ready in this? So plus this call, then after you find out which one is ready, you call ready, read, write, except with a file descriptor. So let's go through an example. Again, pseudocode, right? You pass in select, and you pass in the array of connections, which are an array of file systems, right? File descriptors. And let's say this is the only one that is ready. None of them are ready. But what? Guess what? You don't know. If you're here, once this unblocks, by the way, if none of them are ready, you'll be blocked for whatever the timeout specified. If you don't have no timeout, you'll be blocked forever until one of them becomes ready. Once any of them is ready, now you're responsible to do the loop. You're looping through each one of them and calling FD is set. I was like, is it ready? If it's ready, and this is fast, right? Because you actually got back this FD set to actually loop through them. And then you call read, and this will be unblocked. So now technically you will loop, pop, fast, skip. You're skipping through it, and then you get to this, and you're gonna read it, and you'll empty it, as you drain it, and then move on. So that's select. Very simple, but it has certain disadvantages, pros and cons. So what is the pros? The pros is it avoids reading unready resources, as essentially you're not blocked, right? Well, technically you are blocked if you call select and there is nothing ready, but that's like a mini block, right? Because there is a timeout. And the process of that's basically how asynchronous works, right? I'm asynchronous now, slightly better, but the code is like a little bit complex now. I'm doing all this stuff, but it's still slow because I'm looping through all of them to do this if set thing. Right? Can you make it? Can you make it so that the kernel tell me exactly what's ready? Yeah. And another thing is we're copying a lot of stuff from user space to kernel space, because every time you pass in this stuff, you're copying all of this metadata to the kernel. That's an array of set. You're copying it to the kernel and moving it back, copying it back, copying it. So there is like a lot of chattiness. So it's very inefficient. And it only supports a fixed number of files. I think there's 255. It doesn't support more because of the way the kernel builds. All right, let's do something better. EPOL is the standard now. EPOL is basically what people standardized on the Linux stuff for asynchronous operation, right? And that's what Node uses through the library that's called libuv, or libmicrov, I think that's how you read it, right? For asynchronous operation, but it still has some limitation. We'll talk about that. So EPOL. So here's how it works. EPOL works by saying, hey, I'm interested. You register an interest list once. You do this once. Register an interest list. You do this once. You register an interest list. Okay. I'm interested in connection 1, connection 2, and connection 3. That's the first thing you do. Right? And the kernel starts creating this data structure. It's called EPOL create. That's the system you call it. You call it, it's fast, it's one thing, you do it, and that's it. There's a data structure that keeps creating here, and it will start monitoring now. Any packets arriving for connection 3, connection 2, and connection 3, which is incoming, right? Kernel keeps getting data for all these connections. It will start marking those, updating those data structures. Oh, we got data here. We got data here. We got data here. It will start building something called events for the data structure as it arrives, because this is happening regardless, right? So as this happens, it will add entries to your data structure that you are in the interest list, right? And some of the interest list, some of the items in interest list will be empty. Some of them will have events, as in something just got in, right? So that's the thing that's happening on the background. So then the process calls something called equal wait, which is similar to the select thing. So all right, call equal wait. That's the third thing that happens. And what that does is like an immediate return by the kernel. So it's still, we're copying stuff, but we're only copying things that are ready. So all right, let's loop through all of this, the interest list. Oh, we have this ready, this ready, this ready. Let's create a data structure special and then return the list of events. And happen in this case, only one item in the interest list has it, which is connection 3 and has some data. Boom, return an array of ready list. All right, let's go through an example. So here, this is the equal E in this particular case, in the kernel. Here's my 10 connections, and I create an equal and I pass in all these beautiful connections. Boom. All these connections. You get a beautiful E here. And that's your equal structure. Then you call equal control, right? Here, that's another option here. So you created, you can pass the connection if you want, but what if you want to later add more connections? You can add more connections or more, or remove, for example, you can do it through this equal control and you can add more. So I just added it to show you that you can actually add, right? You're not stuck just by the creation. You created once. Remember, the equal creates once, and this can be changed as you have more connections to be interested in. Meanwhile, the kernel is receiving and receiving data, receiving. And so this is an infinite loop. You call equal wait, right? We'll go there through that next. Meanwhile, receiving data. What did we receive? Well, we received some data on connection 4, some data on connection 9. Look what happened. The kernel only creates a new entry. He said, all right, we have a ready list for connection 4 or connection 9. That's it. So literally a pointer and creates an entry. Sweet. That's beautiful. Then the kernel, the process calls equal wait. That's a system. That's another syscall. So we have one syscall, another syscall, another syscall. So he's still talking to the kernel. There's still chattiness. There's still switching from kernel mode to user mode, right? And that's all right. Give me the events. What do I have? And immediately here, we know that there are 2 items. Boom, we loop. We empty that list and we loop just on those 2 items, just on those 2 events, which happens to be connection 4 and connection 9, right? So that's powerful. People love this because, hey, big O of, it's not big O of N. I don't loop through everything, right? There is no big O of N. This is really efficient. Eh? The inefficient part is the constant syscalls. We're still calling ewait, people ewait, right? So there is drawbacks to this, of course, and it's really complex. And I showed you part of the code. The code is like a little bit more complex to write, right? So there is like this thing that's called level triggered and then edge triggered, and honestly, I keep forgetting the difference between the two. I think there is like a level triggered and edge triggered. Yeah, if I remember correctly, level trigger like will bother you every time. Let's say you have a connection that keeps receiving data. So that means you're gonna always get an event from that, right? Connection, which is kind of unnecessarily, right? So there is an overhead to that, right? Because connection 3 is always ready, right? So you're consuming an event entry for it, and you're iterating over it, right? So edge triggered, on the other hand, and the kernel is also maintaining the data structure behind it, right? It's like always updating it. So edge triggered is only tracks changes. Like if there's always data, I'm gonna notify you once, right? And then I'm not gonna notify you again. unless something changed, unless it becomes not ready, then I'm gonna notify you, right? So that is more efficient to the kernel, but it adds complexity to the user, because the user have to track, oh, what was this now? Was it now? Was it ready or not? You have to keep all of this stuff. So a level trigger is way easier, of course, but edge trigger is more efficient. But the client has to know all of this. And of course, this is only available on Linux. It's not on Windows. And the disadvantage, the drawbacks, is system calls. Yeah, too many system calls. System calls are expensive. So many system calls means you're switching constantly from kernel mode to user mode. And we talked about how that causes, actually we're going to talk about that more. But essentially it causes, like, we're flushing some registers and we're freeing some registers for the kernel mode for security reasons. So yeah, there is a little bit of an extra overhead when you do a kernel switch mode to do the system call. And doesn't work on files because there's no concept of readiness, because this is again ready, right? Because hey, I received the connection, I received the data, I became ready. It was not ready, now it's ready, right? But files are always ready. I was like, oh, you cannot do asynchronous IO based on a ready based on files, because they're there. Just read them. It just takes time. All right, let's talk about IOUring. So IOUring is the example I picked for completionist based. The kernel does the job here. And it's based on shared memory. User and kernel shares space, and that's basically what the biggest disadvantage of this is, because of the shared memory. And biggest advantage, because of shared memory, there's zero copy. Right? I don't need to copy things around. Kernel and user share one area, and they are literally reading from the same thing. So there is no much system calls going on. That's a good thing. But the bad thing is security. Right? We'll come to that. They removed the overhead of kernel mode by adding shared memory. Right? We'll talk about how this happens. Kernel does the work and write the results. How? Let's disappear for a second. Can I actually, because I want you to see my hand waving. Yeah. So let's talk through this. Here is how it works. We have the process, and we have the kernel on bottom, and then we have the user at the top. Well, technically, and they share memory. There is a shared area that is allocated by IOUring where user can write and our kernel can write and read from the same memory accessible by both. And you do certain methods to write to, and in this shared memory there is two queues. There is the submission queue and there is the completion queue. So you submit any job you want. A read for a file, a write to a file, and accept anything. Just specify what do you want in the submit queue. So a process writes a job to the submission queue tail. It goes to the end. And the kernel reads it from the head. The kernel will pull a job, executes it when it's ready, when it feels ready, and then when it's done, the kernel writes the completed job to the tail, and the process keeps consuming the jobs that are completed from the head. Very simple design, elegant. And each job is assigned, I call it job, but I don't know if that's what it is. Each job is assigned and a unique identifier so that you can know that, oh, this is the job I actually submitted. So you know which one is which, right? That's basically it. So you go here, go up the way here. Here and here, right? So write is just a copy, right? You're copying directly to memory here. That's it. And this is just a read, and you're not really copying it again to somewhere else. Well, maybe the kernel decides to copy this just temporarily somewhere to start execution, but it can actually read this stuff. So yeah, it is fast, it's non-blocking, but there's a huge security issue when it comes to shared memory, and people found all sorts of stuff. Google limiting I/O urine due to security vulnerabilities. This was June 2023. While I/O urine has been one of the greatest Linux kernel innovation in recent years for helping to deliver more performant and efficient I/O, it also been home to various security vulnerabilities. Due to ongoing security issues, this interface for asynchronous I/O is being restricted for outright disabled across Google products. The Google security blog noted that 60% of submission of the Google vulnerability rewards have been around I/O urine. Google has paid out $1 million worth of I/O urine vulnerabilities from its reward program. Look at that. All of this for I/O urine. So they spend a lot of money with it. Said, you know what? Let's disable this thing. But this could be a good thing, to be honest, right? We're flushing all the bugs, but eventually it's going to become secure. But yeah, so this is like all the, how much, if the FS library, the net library, and then I/O urine. Look at that. Total reward, number of exploits. So many, 15 exploits as a total of $1 million. As a result, 1 million is nothing for Google. Come on, Google. As a result, Google has disabled I/O urine in Chrome OS until finding a means to probably sandbox it. Google Android, meanwhile, is using a seccomp BPF filter so that apps cannot use it while future Android develop. So what does the security blog say? While I bring performance benefit and promptly reacts to security issues with comprehensive security fixtures like backporting 5.1.15 to 5.10 stable tree, it is fairly new part of the kernel. As such, I/O urine continues to be actively developed, but it's still affected by severe vulnerabilities. For this reason, we currently disable. It's disabled for now. Maybe you're watching this course, you're listening to this course in 2025 or 6, and this is all enabled and this is the default. Who knows? All right, cross-platform. How do I be cross-platform? Like in Windows, they use event ports, which is in Windows they use ISMP and EPOL Linux and KQ and whatever in Mac. So how do we deal with that? So no one just decided, you know, there is this library out there that's beautiful. It's called libuv, and does take care of all the asynchronous I/O for you. You want to read it from a network? If you're on Windows, I'll just abstract all this away from you. If you're on Linux, I'm gonna use EPOL. If I'm on Mac, I'm gonna use KQ, right? Which is another ready event. If I'm in there, I'm gonna use event ports. I don't know what event ports. Maybe it's BSD, I think. IOCM. If you're Windows, I go and use IOCP, which is a completionist, just like I/O urine, not just like it, very similar. Right? If you want to read it from file, don't worry. I have a way to always make it asynchronous and non-blocking. I'll spin up a new thread and I'll give your file read operation on that thread, so your main thread will become unblocked. DNS, I'll do it also in another thread. User code, certain user code like crypto and stuff like that, cryptographic operation, I'll do it in a thread pool. So there is a thread pool. That's when people say node is multi-threaded, they mean this. That's what they mean, right? Right. Of course, you can spin up a thread if you want a node, but by default, node is a single threaded unless you're doing any of these three operations. Then it's going to use a thread pool in certain situation. Summary. So some kernel syscalls are blocking. We need to be asynchronous in certain cases. This puts the process to sleep. That's not nice. We need to be asynchronous in certain cases. There is a ready based, there is a completion based. Maybe you, the listener or the watcher, the student, maybe you will invent your own new approach that will, maybe you will think outside the box and you'll not think in terms of synchronous and asynchronous. You'll write your own operating system to avoid all of this stuff. Keep it open. See you in the next one.